Hello, welcome to this demonstration. I'm going to be showing the laminar boundary layer theory on a airflow over a horizontal thin flat plate. I already actually did this demonstration. However, for some reason the audio was messed up, so I'm going to kind of just fly through what I already have because I really don't want to repeat everything again. So first we'll open up the geometry. You'll want to do it in Design Modeler. Now the flat plate is going to be 6 inches by 0.1 inches thick. All the conditions are at sea level, and the free stream velocity is going to be 15 meters a second. So the first thing that I did was on the XY axis, I created the thin plate by pulling it down and to the right so that the top of the plate is um, equivalent to the X axis, so that later on when we're inserting some locations, it's easier to plot those locations. Um, so the measurements are oops, let's go back. H1 is going to be 6 inches. The V2 is going to be 0.1 thick. The V4 thickness of the um, wind tunnel is going to be 5 inches by 12 inches. The 5 inches to 0.1 is approximately 3% of blockage ratio, so I thought that worked perfectly fine. And then you do concept surface from sketch, click on the one of the lines, and it'll create this sketch for you. Next, we'll close this and go to the meshing. Alright, so it'll load this in, and then you'll begin with your mesh. The first step is you'll not have any of these. So the first step is add all triangles method. So you'll basically right click, insert method, and it'll be default selected on the method of quadrilateral dominant. You'll want to choose triangle and then generate that. It'll generate all these little triangles, but it won't be so fine. It'll just be large like these. So what we'll do next is do an inflation. The inflation is going to be only on the edges of the flat plate. So you'll control click all of the edges. You'll have 4 edges total. You'll do a smooth transition with default transition ratio, maximum layer of 5, and the growth rate is going to be default of 1.2. So when you generate that, if I zoom in here, you can see these little rectangle inflations out, and that's basically the inflation around uh, the plate itself. Next, we'll do an edge sizing. The edge sizing is going to be on the plate again. You're going to choose every single edge, and we're going to do element size um, at 6.5 e to the negative 3 inches. We're going to make the behavior hard so it doesn't capture any curvature. Since we're doing a flat plate, we want to capture those hard edges around the plate. And then, again, once it generates that, it's going to be super fine, as you can see here. Very fine meshing around the plate. And then lastly, I want to make sure that the velocity on the inlet and the outlet are captured nicely on the meshing. So we'll do an edge sizing on the inlet and outlet of 6.5 e to the negative 2 inches. Same hard behavior. Doesn't really matter, I don't think, that much since it's the wind tunnel portion, but I just keep it consistent. And you'll end up with this meshing here. Then after that, we'll go through the naming selection. So you'll make sure that you're on edge selection, and you click on each edge to name it. And if you want to click multiple, you'll do control and click both edges or multiple edges that you want. So for example, inlet, I just did the one. Outlet, symmetry is an example of 2, so you want the top and the bottom of the wind tunnel. So you'll just click that and then hold control, click that, and you should be able to do both to name it. Then I went ahead and did the front, top, bottom, and back for the plates, and that is it for the naming section. So the mesh is complete with that. So we'll close that and go to the setup. For setup, we'll do double precision with 4 solver processes. We'll open that. It'll take a second to load in the meshing. Great. So you'll see the mesh here. And for this model, I ended up using the K epsilon model. And then we did enhanced wall treatment and pressure gradient effects on and left everything else default. Nothing else under model. Material, we'll check air. And for my project, I was working at air at sea level conditions, so I just left the default density and viscosity in there. And then boundary conditions, I was doing 15 meters a second and then 30 meters a second. So for this demonstration, I was just doing the 15 meters a second. So that's why I inputted that there. Next, your reference values, you compute from the inlet, leave all of these defaulted. Reference zone is going to be the surface body. Methods, we leave these defaulted. Report definitions, you can go ahead and add your report definitions if you want to calculate the drag force coefficients, the skin friction coefficient. You can get your Reynolds number from here. So basically we'll do drag. You can do the drag coefficient or drag force on, I did the top plate, or you can do all of it. I'll do all of it actually. Now you have your report definition there. You can rename it if you'd like. I just left it the same. And then initialization, I always change my initialization to 25 iterations. Initialize that. And then lastly, our calculation, I always do like 500 iterations or more. For my actual project, usually I do a little bit more iterations so it's more exact, but sometimes it cuts off the program anyway. So I'll go ahead and calculate that. And then once this is complete, I'll move over to the post. Now from your reports, you can compute that and do your calculations depending on what terms you would like. These are some of the different ones. All right. Now as far as post goes, we had to show the contours for the velocity, the pressure, and actually not even the pressure, just the velocity and the velocity vectors. So yeah, so created a velocity contour here. What you do to do that is click on this contour, rename it to velocity contour if you'd like, or whatever you might need to find. Locations is going to be symmetry 1. As you can see, it highlights everything, and that's what you want to see. Then we did the velocity U, global, 100 of contours. The more contours you do, the more precise it'll be. I can kind of demonstrate that too. You can see how bad this looks compared to 100. But it actually kind of shows almost the boundary layer forming. Kind of see that there. Anyway, go back to 100. Zoom in, and let me move the legend out of the way. Great. So here you can see a very low velocity. It's stagnant. This is the stagnation point right in the front. And then there's also another kind of reversal happening here. I don't know if that's because of my model or just the inherent ANSYS program, but I think this is somewhat to do with my error in the calculations. But disregarding that, you can see the boundary layer forming and expanding as it continues. You have a very high velocity here because this is acting like a nozzle. And then as we come to the back, it's acting like a diffuser somewhat. So then we have a really low velocity here, high pressure region. And so that is your velocity contour. Now if you want to see the vectors, you would do vector here. I already have mine here. So you'll add in that, do symmetry 1 again, vertex reduction factor, velocity, and then to get this nice appearance here, you actually have to change the size of the symbols. So I did line arrows at 0.1. I think at default it's 1. Yeah, default it's at 1, so it looks insane. But if you do it to 0.1, it makes them smaller and more comprehensible, and it helps you see the boundary layer forming and how the velocity is 0 on the wall because of the no slope condition. And then also here you can see the stagnation point where it's basically it's 0 right here and very slow as it kind of creeps around and then speeds up here because of the nozzle effect. And on the back we can also see like that circulation that I was mentioning definitely messed with my calculations, and I think I'll try to look into a solution for that. So anyway, that's the vector lines. Next, what we'll do is we want to see the boundary layer velocity profiles. We wanted to see it at the endpoint and the midpoint. So I created the endpoint and midpoint here, these two yellow lines. The midpoint, since this post is in meters, I had to do the unit conversion from inches to meters. So for the midpoint, half of 6 is 3, so 3 inches in meters is 0.0762. You'll do that for the x, so that is the same. And I only did the y up to 0.1 because if you see the velocity contour, once it's that yellow line is basically out of the boundary layer, so kind of left it at that. And then did 100 samples, and the same thing for the endpoint. Now the endpoint is at 6 inches, so it is 0.1524 when you convert it to meters, and the same thing, I did 0.01, kept it consistent. And then lastly, I'll show you, or not lastly, I'll show you the velocity profile. So to create a velocity profile, you'll go to chart, name it velocity profiles, and then the midpoint and endpoint, those lines that you created are essentially the data series. So those 100, if I go back to this, those 100 samples are the data points that it's collecting for your velocity profiles. So you'll input that. You can rename them if you want. I just left them because it doesn't really matter. The x-axis is going to be your velocity, u, at that point, due to the y, so the height. So off the height, as the height changes, the velocity changes, since it's going from the basically the top of the plate at 0 velocity all the way up to the boundary layer, and then it's going to go to that free stream velocity value of 15 meters a second. So as you can see here, the red is going to be series 1. So series 1 is the midpoint at 3 inches, and series 2 is the endpoint at 6 inches. Great. So now that is the velocity profiles. We'll move on to the shear stress charts, but first we have to go back and make another line. I'm going to deselect the mid and end points and show you the top plate line. That's what I called it. So to see the shear stress on the top of the plate, you want it to be on top of the plate. So basically go from 0 all the way to 6 inches, and at a height of 0, since it's right on that axis, and converting it to 6 inches is 0.1524, and I only did 100 samples. You can do more if you'd like. So I'll deselect that. Doesn't really matter. But now I can show you the shear stress. It's going to be the same charting. you'll input that data series, the top plate, and since we're going along the top of the plate, it's going to be changing on the X variable, and the wall shear is respect to the Y axis. And as I mentioned earlier, I think these weird charting points, kind of like right at the front and right at the back, is due to these recirculation points. I think that kind of messes with the wall shear calculations for ANSYS. So again, I'll try to fix that maybe in a future project. But for now, it'll have to do because I've exhausted all my options, and this is what I can come up with at the time. So that is the charting for shear stress. What else? Alright, so I can also show how to relate it to the Blasius concept or idea. We'll go back to our velocity profiles, and what I did was added a expression. So we'll do new. I'm just going to call this the Blasius velocity. So it's going to be velocity in relation to the height divided by our free stream velocity. So it's going to be little u divided by u infinity, and in this case it's going to be 15 meters a second. I might have changed velocity. I'm going to pause this for a second and see what I'm doing wrong here. Alright, so I figured it out. You have to do a capital V for velocity, and then it'll italicize it. I wasn't doing that, so it wasn't working. So once you hit apply, you'll see it's in meters per second. It'll give you the right units. And then now you can see the Blasius velocity is here, which is just, again, little u divided by the free stream velocity, u infinity. We'll go back to our variables and add a new one. I'm just going to call this Blasius velocity again. I don't know. And the expression is going to be Blasius velocity. Apply. Oh, it can't be the same name. So I'll just call this BV for Blasius velocity, whatever. And Blasius velocity. Okay, so now we have Blasius velocity BV as a variable. We'll go back to chart viewer, and our x-axis, instead of velocity u, we'll change it to the Blasius velocity. There we go. I think I might have not been on the right page. So once you do that, it'll make a relation to 1, and from 1 you can figure out where your boundary layer thickness is approximately. You can export all these values, and then knowing that the boundary layer is approximately 0.99 of the free stream velocity, you can figure out where the boundary layer thickness is for the midpoint and the endpoint. So it's probably about around here or so, but by exporting it and doing those simple calculations, you can figure out approximately where the boundary layer thickness lies. also, if there's anything else, you basically just export all of your files for further calculations, and you can figure out your laminar, your Reynolds numbers. Um, you can figure out the wall shear stress, the local skin friction coefficient, your drag force coefficient, so all of those things through either post ANSYS or within Fluent itself. So, thank you for watching.